Okay. Good afternoon. See, in this particular period, we will look at what is called Kelvin's theorem for calculation of dissipated energy during central impact, right? So that's what we'll see. Let me just share my screen for that purpose. Hope you're able to see the screen. This is lecture number 13. In 21/07/21. We will study about what is this Kelvin's theorem. Kelvin's theorem for dissipated energy during collision. See, what is the theorem state? So during collision means, see, I use this mathematical definition of that. So delta E is energy loss due to dissipation. So I just put that with the prime, right? So in the previous class also we have seen delta E, that is energy loss we have calculated, where we have not put with the prime dash, right? You remember that in the morning class we calculated the energy loss percentage. So here it is delta E dash called dissipation energy during collision, and that would be given by total impulse during the collision multiplied by P plus P dash by 2. So IMP is what is called the total impulse during collision, and within bracket I have P plus P dash. So what is this P and P dash? This P is relative velocity of approach. And what is P dash is relative velocity of separation just after the collision. So the theorem states the energy dissipated during collision is given by the product of total impulse present in the system multiplied by sum of the 1/2 of sum of the two relative velocities P and P dash, right? So this one, to understand what is that we are going to do at the end of this period is we are going to just look at what is total crush energy. So in that, if you look at, I just put delta E without dash is what is total crush energy. So when I say total crush energy, this is that the total energy that is possessed by your vehicle. And from that, you have the energy dissipated is what is delta E dash. And you will be able to derive the relationship now at the end of this period as this. This delta E dash is going to be delta E into 1 minus E square. So the dissipated energy, which is stated by the Kelvin's theorem, is finally would end up with the relationship of total crush energy multiplied by 1 minus E squared, where E is coefficient of restitution. So we are just going to look at how this relationship is obtained, is what we have to do. So that understanding to do, we are going to do an approach called the relative velocity motion approach. So we need to start with the basics again to understand what is this relative motion. Let me just explain you. Let us look at space, and I'm looking at space with this coordinate system x, y, say z. I have here a trajectory, a path. I have here a vehicle A, and see another path. I have vehicle B. So these will have their velocities, their motion along this path. Say the position at any point of time can be represented with respect to the space. So space is one of the fundamental concept of mechanics. So with respect to this reference, I can give position at any point of time. Where is this vehicle A located? And that would be RA vector. So what is RA vector? So RA vector would be xi, xai plus yaj plus zak. So it's position vector. So the coordinate here at any time t, that is another concept of mechanics. Space and time are two important concepts of mechanics. Other two are mass and force. We have seen that already. So this coordinate is xa, ya, and za, right? Similarly, I'll have here its coordinate, and I can have its relative position with respect to the position vector rb. So any vehicles are in motion, whether it is in space or on ground, can be represented with respect to a fixed reference on the ground, one shown here like that, Cartesian coordinate. So with respect to this point O, I can look at their motion, and I can give at any point of time their positions by RA. So if this RA gets to another position, I can define its change of position with respect to time, is what is velocity, and then rate of change of velocity with respect to time, what is acceleration, and so on. We don't go into that. Now to understand what is relative motion, let's look at now the motion of A with respect to B. So I look at now motion of A with respect to B means, now I have here in vehicle B a moving reference. So being from this moving reference, I look at A is what is called relative motion. So this is RAB. So motion of A with respect to B is what is given by this. So now what is relative motion concept? So concept of relative motion is, if I have to express absolute motion of say any one of this, say I need an absolute motion of RA vehicle, I can get that from the instruction given to the ground station from a fighter aircraft A, B, say, for example. So they say for the fighter aircraft, the velocity or the motion appears of the enemy's flight A as RAB, its position. If this is informed, I know being from the ground, the B of my vehicle is controlled, so I can predict what is its absolute velocity. So this instruction given to the ground would hit this vehicle. So that is what is the concept of relative motion. So how do you get that? So it's simple vector addition. So RA vector would be RB vector plus this. So it is going to be RB vector plus RA with respect to B vector. Or if you want to write the relative velocity or relative position RA with respect to B, then it is going to be RA minus RB vector. Right, so what is this going to be? It is XA minus XB into I plus YA minus YB into J plus ZA minus ZB into K. So that is what is RAB. Here this XA, XB these coordinates are function of time. So this is all the representation on this picture is just at any time t. So if we look at another time, then this will be changing. So these all are function of time. So these position vectors are function of time. So if I differentiate the position vector with respect to time, I'll get velocity vector. So I can rewrite this same for velocity as well. So this equation can be written for VA vector as equal to VB vector plus VA with respect to B vector, like this. And I can rewrite similarly velocity of A with respect to B is what is VA vector minus VB vector, right? So you see this equation is what is relative velocity vector. So now in Kelvin's equation theorem, we have small p. So that small p is representing V1 minus V2, where V1 and V2 are velocities of two vehicles in direct central impact before collision. So velocity of 1 with respect to 2 is what is the relative velocity p. So what is p dash? It is v1 dash minus v2 dash. So this sum p plus p dash, half the value of that is multiplied by the total impulse present in the system, that would be equal to total dissipated energy. That is what is Kelvin's theorem now. So what is this P and P dash to follow? I just have explained you what is this understanding of concept of relative motion. If anybody of you do not understand, you can ask me. And here you see this is a generic explanation. So if it is one-dimensional motion like direct central impact, that's become simplified. If it is curvilinear motion in a plane, then I will have only two components. So that's further simplified. But vectorially, if you represent the motion parameters, that has got an advantage of accounting complex space motion. So this is generic way to represent what do you mean by relative motion. So relative motion is you have system of particles, system of vehicles moving in space or on the road, highways. You represent their motion with respect to a fixed reference called an absolute motion. But as you look at two vehicles colliding, the driver who is hitting the vehicle of the front vehicle because he's accelerating and suddenly is slowing down and from rear he is hitting. In such cases, what is that the driver's point of view who hits the vehicle is what is relative velocity. So what is the velocity of the head vehicle with respect to the person who is driving is what is relative velocity, right? So that is what is important. So I hope you understood what is relative motion. And now we will get into our derivation of proving this Kelvin's theorem for dissipated energy, right? So for that, let's look at now relative motion during impact. I'm going to take relative motion during impact. So let's look at now my P is V12, which is equal to V1 minus V2. So this is relative approach velocity. This is called a relative approach velocity. And P dash is what is V12 dash. Otherwise, it is V1 dash minus V2 dash. So that is relative separation velocity. Relative separation velocity. So relative separation velocity by relative approach velocity is what is that is defining coefficient of restitution. So that's going to be P dash by P, right? This is also that you know that we have looked at. So I would get P dash given by E times P. Okay, so now if this is the case, we can have motion under consideration now of three different cases. So I'm going to explain one by one. Let's just look at case one, where I have two vehicles. So let me take this is vehicle 1, so this is M1, and then there's another vehicle M2. So these two are going with some velocity. This is V2 and V1. Both of them going to the right. So always consider this is positive. To the right positive convention velocities all the time. Any positive value of velocity refer to the motion of the vehicle to the right. So if we consider this, this would be one case. Or it can be that this vehicle can be at rest. So, or third case is, say second case is, so this vehicle M1 with velocity V1, whereas this is under rest. M2, V2 is 0. So this is case 2. This is case 1, this is case 2, and this is, whereas one more case 3, we can have this M1 with the velocity V1 and M2 mass with the velocity approaching towards this V2. So the direction of this velocity is, you see, it is along negative direction. So these are the three cases that can be possible for configuration of direct central impact. So why did I draw this and explain you this relative velocity concept is said? If you look at this relative velocity V as function of time, so I'm not looking at an individual velocity, rather I look at the relative velocity P. In any of this case, you can look at what is this P as function of time. So you know the entire event gets over in milliseconds, right? So I just have a time T1 before and after collision. So initially the relative velocity suppose is this much, and that would be reduces. So the variation of this relative velocity during the collision would be something like that, like this, something like this. So you see there is a point where you have the time let's call TCV, and this is 0 value, and you have here again this velocity comes down and this goes here. So this is corresponding to P dash. So whatever that I measure from 0 here is what is P velocity, and what is there here it is measured is P dash. P dash is again a velocity of separation velocity. So there is a point where you have the relative velocity is 0, right? And that point is corresponding to a time of common velocity. That is the reason why subscript CV you have. So CV refer to common velocity. So here we have to make some of the clear understanding always that this P is always positive. This P is always positive before collision and negative after collision. So this P is always positive before collision and negative after collision, right? So V1 dash minus V2 dash is always negative. So what does that implies that the velocity of V2 dash is always greater than velocity of V1 dash after the collision. So in every case, there is a point like you see here, P is 0 at some point during the collision. And if you look at this common velocity time itself, this point what is there here is what is in milliseconds, that is that crash event, right? And this point is corresponding to called the maximum dynamic crash. So this also in textbook referred as TM, corresponding to maximum dynamic crash. Maximum dynamic crash corresponding to that is what is the TCV. At that time, you see this relative velocity is 0, right? And after that, it's become negative. That means it's separation velocity. So separation velocity here I have written it's V1 dash minus V2 dash. So that's happened to be negative always. So it is obvious that V2 dash is greater than V1 dash in every case, right? So that is what. So P dash is always negative. Always negative. Right? And this is what is TCV is a momentarily the common velocity. So after that, there is no velocity. So at this point, when P is 0 means what? P is 0 means V1 minus V2 or V1 and V2 are of same velocity. Then only it will be. Or V1 dash or V2 dash should be same. That is the point where it is a momentarily common velocity with which it moves. Right? So this common velocity point explains you clearly the two phases of your dynamic crash event, that is deformation phase and the restitution phase, right? The vehicle crash is at its maximum value. So the TCV corresponds to maximum crash, maximum vehicle crash. What is that maximum vehicle crash? That is end of deformation phase. End of deformation phase. End of deformation phase. So at this deformation phase, right? At this deformation phase, you have what? You have plastic or elastic impact. So deformation phase would involve plastic and elastic impact. It is not only, it is beginning of deformation, maximum value, and then it is restitution. All accounting together is what is this TCV, common velocity point. So what is that? It is also the phase, restitution phase begins at this time. Actually, TCV is the time where the maximum vehicle crash or the end of deformation phase, you can say, or it is the beginning of restitution phase, you can say, where in beginning of restitution phase continues and then total separation of the vehicle takes place. So when I say beginning of restitution phase, it is going to be only elastic deformation. It has to be very clear. So when you say deformation phase, that will involve the structure which are under engagement during collision to undergo plastic and elastic deformation, whereas in restitution phase, it is only elastic deformation or regaining of elastic deformation. There is no plastic deformation that is taking place at that time because the maximum deflection occurs end of deformation phase. Right. So now you see this during this time TCV, they exchange an impulse forces. They exchange two masses exert and impulse forces that we have seen. And these forces are both dissipative, losing energy, dissipating and losing energy primarily on the deformation of the bodies, and non-dissipative, storing or releasing energy right? Releasing energy during restitution phase. So the integral of these forces over the time is what is the total impulse. So the total impulse can be obtained by integral f dt. That's what we have seen already, f dt. So let's look at that from t to t dash. So where here f is the exchange of collision force. So again here important thing, the colliding vehicle, after the vehicle struck on the other vehicle, the brakes are released. So they are free, their frictional impulse forces are negligible. So you can consider along the line of impact, momentum is conserved. So we were doing that earlier derivation, the exchange of impulses are cancelling each other. That is why linear conservation of linear momentum is applicable in line of impact. If this if the exchanging surfaces additionally has got some friction, if that is not smooth surface friction, then you have an external additional impulses, then the momentum cannot be conserved. So the basic assumption that we had so far is in central impact we consider the vehicles are not with after the as soon as that vehicle hit the vehicle, supposing it is stationary vehicle, after the hit the vehicle brakes or hand brakes are released, it is not on. So if it is released, then only it will be freely going, then consideration of linear momentum along the line of impact is applicable. So that you have to keep in mind. So now in this this f is what is impulse force, and IMP is what is total linear impulse. So now applying principle of impulse and momentum on two vehicles. So we have considered what we have considered the case where you have the first case. Look at here. Let's just imagine the very first case. We have also earlier represented this as two spheres. So let's consider first case that V1 is greater than V2. So at one point of time it's going to hit. Then I can apply now linear impulse and momentum principle. That would give me m1 v1 minus total impulse exerted by vehicle v2 on v1, that's equal to m1 v1 dash. So I just take vehicle 1 alone and write this equation like we did earlier, and then second equation would be what, m2 v2 plus imp equal to m2 v2 dash. So if you look at what is the difference from earlier class and now I'm doing it is, earlier class I was taking the same and again from the common velocity point I was doing it. Instead now I'm taking one particle, one vehicle and writing impulse on momentum principle, and second vehicle also I'm doing. So second vehicle when I write, the impulse is exerted by A onto B. So the sign would be changed here. That's what these two. In this V1 and V2 are initial velocities of mass 1 and 2. V1 dash and V2 dash are the final velocities after collision for mass 1 and 2. So considering 1D motion. So 1D motion here is one-dimensional motion is direct 1D motion in the textbook. If you look at that, refer to what? Direct central impact. So direct central impact, considering, I can write now what is the total energy before and after. So before collision, what is the total energy? It is half into m into v1 square plus half into m2 into m1 m2 into v2 square, and that would be equal to the kinetic energy of m v1 square plus v1 dash square and half m v2 dash square. Energy is not conserved. So the total energy before collision. After that, if you look at this energy from the v1 dash and v2 dash, which you can find out from the definition of E. So for that you can use this, but I'm not using now to define E, rather to define energy loss. That is why I take both the vehicle and apply in this fashion. Right, in a previous derivation, direct central impact, first equation we write first consideration of linear momentum equation. Next equation we write definition of restitution. We derive definition of restitution, coefficient of restitution, and then we used. So V1 dash and V2 dash are known. I know what is the total kinetic energy of the system, and that won't be conserved. So I would have the remaining part as my energy dissipated. So that is what is deferred by delta E dash. So this is all exercise we do it to prove what is Kelvin's theorem. So this is now equation number 3. So what is this? This is that energy dissipated during collision process. So I'm just going to play around with these terms exchanging. So I'm going to take now V1 dash, this kinetic energy term on this right side and this onto the left side. I would get my expression like this. So M1 by 2 into V1 square. And here it comes, it is V1 dash square. So V1 square minus V1 dash square, I can rewrite it as V1 minus V2. Sorry, V1 minus V1 dash into V1 plus V2, right? On the other side, I take this term on the kinetic energy of second vehicle on the other side. I would have M, this is M1, M2. I would have here M2 by 2, and here already it is V2 dash, and this comes, it is minus term there. So V2 dash minus V1, V2 dash square minus V2 square. So I will write that as V2 dash minus V2 into V2 dash plus V2 plus delta E dash. So this is my equation 4, right? So why did I write this? Is to look at now from equation 1 and 2, I can get these expressions. So from equation 1 and 2, since it is M1, I can have my V1 minus V1 dash. So I will take M1 V1 dash on this side and total impulse on this side. What is that is going to be? From equation 1, I get V1 minus V1 dash as IMP, total impulse by M1. Similarly, the equation 2 I get V2 dash minus V2 as equal to IMP by M2. So now these two I can substitute on these, and then I will rewrite this equation. So this equation become on this side I substitute this. So V1 minus V1 dash, I replace this with this. So M1 goes off. So I'll get the IMP by 2 into V1 plus V2 on one side. On the other side, I'll have IMP by 2. And this will be V2 dash plus V2 plus energy dissipated. So this is that now equation number 5. Still to get for now delta E dash, let us take this term on the other side and holding on one side delta E dash and bringing these two terms together. What would happen now? Look at. So this become minus on this side. So I will have V1 minus V2 within bracket IMP by 2 within bracket. I'll have V1 minus V2 plus this goes on that side. So it is going to be minus V2 dash. Here V2 is there. So V2 V1 I club with this V1 minus V2 and V1 dash minus V2 dash now. So it's proved now. That's equal to IMP by 2, where V1 minus V2 is the relative velocity of approach. V1 dash minus V2 dash is relative velocity of separation. It's very simple derivation, and this is what is called Kelvin's theorem for dissipated energy. So now continuing with this further, you would be able to have two cases. See, the two special cases are, so one is now I have this equation number 7, that is delta E dash is equal to IMP total impulse divided by 2 into P plus P dash. That is equation number 7. And equation number 8 would be the relationship between this P dash is what is E into P. That is equation 8, relating coefficient of restitution. So now we know this E value would be between 1, 0 and 1. This is what also we know. And we know if E happens to be 1, it is perfectly elastic impact. E happens to be 0, it is perfectly plastic impact. This all we have already discussed. So now what I want to do is I want to get my velocities V1 and V2. V1 and V2 for this. So how do I get V1 and V2? Let's take equation 1 and 2 again. So equation 1 is what is application of impulse equation. So initial impulse plus initial momentum plus impulse is equal to final momentum. So equation 1 would give me what is V1 velocity. Equation 2 I will write what is velocity of V2. So from this I would get now from equation 1 and 2 I will get what is V1. So V1 would be equal to total impulse by M1 plus V1 dash, and V2 would be minus IMP by M2 plus V2 dash. So this, let's have this is equation number 9. And now I would write from this, what is P? So P is relative velocity V1 minus V2. And I would now subtract this one from the other. I would have IMP by M1 plus V1 dash minus of minus become plus IMP by M2 minus V2 dash. So what is that I have now? If I take these two terms and IMP by M1, IMP if I take it's 1 by M1 plus 1 by M2 and plus V1 dash minus V2 dash. So here it's very interesting concept. Morning we have seen one of the key word is effective mass. Effective mass is what is two vehicle mass is written now. So this can be replaced by IMP now. Let us take this as the M1, M2 LCM. So I'll have M1 plus M2. Here what is V1 dash minus V2? That is P dash. This P dash. So this side V1 minus V2 is P. So now we see this, I am going to rewrite this as this. This let us call this equation as 10. And I can write now this equation as this. So I want to find what is my total impulse. So for that, let me take it like this. So impulse, total impulse is going to be P dash, if I bring it on that side, P minus P dash and into M1, M2 by M1 plus M2. So here I define what is effective mass as just M1, M2 by M1 plus M2. So if this is effective mass, I can rewrite this as effective mass into P minus P dash is what is the total impulse of the system during the collision. So now let's look at Kelvin's expression and then substitute for this. So I have now this equation, let's call equation 11. Now Kelvin's theorem is delta E dash is Im P by 2 into P plus P dash. So let me put now IMP by this. So that's going to be ME by 2 P minus P dash into P plus P dash. So I would have this is ME by 2 P squared minus P dash square, P squared minus P dash square. So we have this relationship P dash is E into P, right? E into P. If I substitute that here, I would have ME by 2 P into 1 minus E square. 1 minus E square. So this is what we were looking at the beginning. So and this is P square. This is P square. So ME into what is P square is velocity. So if you look at here, the dissipated energy delta E dash is going to be now half ME P square into 1 minus E square. So this term here, half ME P square, is what is your total crash energy. Total crash energy, delta E. And it is multiplied by 1 minus E square is what is delta E dash. So delta E is total crush energy absorbed. So what is delta E? Let me write that. Here delta E is total crush energy absorbed by the engaging structure of the two vehicles. Engaging structure of the two vehicles involved in the collision. So what is delta E dash now is clear, that is the dissipated energy. Delta E dash prime is now total crush energy dissipated by energy engaging structure of the two vehicles. So this is total crush energy. See, absorbed and dissipated. Something is absorbed and something is dissipated. So this is total energy absorbed and this much is dissipated. So if the dissipated energy is same as that of delta E, that is perfect. That's what we wanted, right? So total crush energy dissipated. Total dissipate. So what is that ideal or ideal requirement? Ideal requirement is delta E dash should be entire delta E. So if it is equivalence of vehicle colliding with full frontal rigid barrier is equivalence of what? A vehicle with the same velocity approaching and they hit. That's what is its equivalence. So if rigid barrier absorbs the entire energy and dissipate that entire energy, then it is a perfect plastic impact. So when that can be possible, this is equal to this when E equal to 0. So this would happen at E equals 0. So what is E equals 0? There is no restitution period. There is no rebound energy. There is no relative velocity of separation. So when there is no relative velocity of separation, they collide and stay there, right? So that is, with the common velocity it goes, and then you will have this condition. So ideal requirement is this, but it is also very interesting that you'll have to carefully see here it is E square term. So generally in vehicle design, E value would see it will be 0.12 or something. So it's very, very lesser than 1 and closer to 0. So when you take like this is already a small value. If I take this value over here, it is squaring again. That's going to be further reducing. So the energy dissipated would be more of the total crush energy. So your vehicle design is such that even you are not able to get E is equal to 0, that's not possible. So you would have your coefficient of restitution is very close to 0. And as far as the energy dissipation point of view is concerned, you see that since there is E square term here, the smaller value further becomes smaller and you have here more. So if it is 0.1, what would be the square? 0.01. So it's 99% is gone, only 1% is rebound velocity. So what is rebound velocity? That is the velocity during restitution period, and that would transfer into the cabin. That would transfer to the occupant. So in rigid barrier test, why do you say is this circled one of MEP square is that the total energy absorbed by the structure is the same as that the total crush energy in the full frontal rigid barrier impact test, right? So this you have to understand. And there are also other observation where you will have your quiz questions based on this. Would be like this. What is that? Is you have an approach speed. Approach speed is squared. Then what would happen to the dissipation energy? So such kind of questions will be there. So you have a rigid barrier and vehicle go and hit with the speed. If this is a rigid barrier, that's V2. V1 is what is its approach velocity? What is relative velocity P? It is V1 minus V2. So let me just explain through this diagram, you would better follow. So I have here a rigid barrier. So this is a rigid barrier. And I have my vehicle towed towards this with some velocity, right? So let's look at, that's my vehicle. And this has been moved here with some velocity. So at the time it hits this point, you have your V1 velocity, right? And it's hit, and then what is this? Is a mass M1 vehicle, mass small m, and this is huge mass capital M. So this is rigid barrier, so this comes and hits here. So what is its linear momentum? mv1 before impact. Here it comes and hits, there is no deformation here. So the velocity of this is v2 is 0. This is 0. Then what is my p? It is v1 minus v2. That's going to be v1 itself. So effective mass when I take this mass ME here would be M into capital M by small m plus capital M. So instead of rigid barrier, if I have a bigger vehicle in this, so this effective mass will decrease. If I take my effective mass, so I account this mass also, then it's simply relative velocity of that square by 2 would be the total kinetic energy. So now why did I say that is because now see this comes here and with the just it is about to hit its velocity v1 is say 30 miles per hour. This is 0. So now 30 miles per hour, if I put it is here square term. So I will have my kinetic energy squared here, right? So if I double the speed, what would happen? If I double the speed, it would become 4 times energy dissipation. That is what it is. Since it is a square term here involved, if this approach velocity 30 miles per hour, instead if I have double the speed as it hits, the energy dissipation would be 2p become. So it's 4 times what would happen at 30 miles per hour. That you have to see, right? It depends on squaring of speed value. But if I have now 2 vehicles going, one vehicle is this M1, another vehicle is this, maybe they are identical vehicle M2, and this is with the velocity V1, which is say 60 miles per hour, and this is going with the velocity 30 miles per hour. So this is V2. So now what is P? It is V1 minus V2. That's 60 minus 30. So again, it is going to be 30, the same direction. So as it hits, so this is very fraction duration. In milliseconds is going to hit like that, you can think. So as it hits, the relative velocity here is V1 minus V2, which is 30 miles per hour. So the effect of this going to be same as that this vehicle hit with 30 miles per hour on a rigid barrier. That's what you have to understand. The speeds may be different. So if this vehicle goes with the 60 and this vehicle goes with the 90, the relative velocity is same. The energy dissipation is the same. That's what you should understand. The speeds may be different when they collide, but the relative speed is constant, is same, and that would come here and it would affect. And this ME is not one vehicle mass, it is an equivalent or effective mass of the two vehicles, and that would be given by this. In this case, it would be ME is M1 M2 by M1 plus M2. So it's very interesting, the concept of effective mass consideration in collision. So you have any doubt at this point of time? I would be answering. If you do not have any doubts, so let's look at the pictures from the textbook. I'll just insert them for your benefit of learning. Just going to take this picture first. Look at this. So this picture now here is the velocities of vehicle, SUV vehicle with the mid-size car hit at 58 miles per hour in central collision. So you can see here the scale in horizontal is in milliseconds. So it's 0 to 150 milliseconds. That's very close to common velocity that we have seen. So we have already looked at a plot where you have your P that would vary like this and it goes like that. We've seen it's a smooth curve. Please pardon for that. This is T, and this is what is TVC that we have seen. So this is P dash and this is P. So like that, typical relative velocity would vary as function of time during the crash event. So now this picture is what is very close to this. At that time scale, we are looking at it, right? So now you see this SUV approach velocity is 58 miles per hour, whereas the other V2, the second vehicle, that is mid size car is of stationary car, 0. So that velocity drops because of the collision, and the stationary vehicle picks the velocity, and there is a common crossover point, and that point is what is common velocity point, VC. So this is that velocity. After that, what is there is separation, so the velocity gets separated, so V2 dash and V1 dash. So you see, this is that what would happen during crash. That is why it is always V2 dash is greater than V1 dash. So V1 and V2. So there are three cases we will see, and you will understand in every case this is happening. Right? And here again, you understand this picture. We will again have to extend this when you have to calculate total crush energy and further beyond Kelvin's theorem to go. Right? So you can see here what is this velocity at the end. Here is V2 dash. And this is V1 dash. So your P dash is this is your P dash. That is V1 dash minus V2 dash. And from here to here, what is there? Is what is your P. So this is P and this is P dash. So P dash is down, always negative, and P is positive here. And this P value can be 0 at some point of time, we say, or it is not necessary to be 0 also. So it's 0 means it has to be, see, it's a real time measurement. So it's not symmetric. But when you make an assumption, then it becomes symmetric at one point. It will be, if I look at only this P variation, then it becomes 0 at one point. But here, since this system of vehicle there and exchange of energies, and you see here this delta V1, what is delta V1 is change in velocity till common velocity. So V1 minus Vc, V1 minus Vc. So this is Vc, this velocity is Vc. So delta V1 here is V1 minus Vc, and delta V2 here is delta V2 is this, that is V2, how do you say that? From this it is V1 dash. How do you write? See, this is V1. V2, delta V2 is Vc itself. V1 minus Vc is delta V1, and V2, this is Vc itself, in this case, Vc. Right? And you also have delta change in velocity of the separated vehicle, delta V1 dash. So delta V1 dash is from here to here. Right? That is V1 dash, V1 dash. How do you understand this graph? Here, similar delta V2 dash. So delta V2 dash is from here. So Vc plus, what is there here? This point is V1 dash, and this point is V2 dash, V1 dash, V2 dash. And there is an overlap here. So it is the V2 dash is given by V2 dash minus P dash. V2 dash minus P dash. And V1 dash is still here, that is V2 dash V1 dash minus. So let me explain this chart later, but you will have next class we'll see this in detail. Right, how do you go about looking at these terms? All right, I would explain. I'm just a bit confused here at this point of time. We'll see that later. And let us also look at now 3 different cases that is called a configuration of collision configuration, right? Possibilities that from the textbook. So let's look at this diagram. Is it visible? Not visible. Okay, take it. So of course, I hope you are having this textbook. You can very well go through, but let me just put this. Look at this chart. This table. So in this table, you would be able to see now 3 cases where mass M1 catching up with mass M2. So it is similar to this. So you have here a vehicle which is catching up with the second vehicle, and it is going to hit from the rear because V1 vector length is greater than V2. So this speed V1 is greater than V2. So relative velocity is P. So this is just before collision, and this two together with the VC velocity, that's this point, and then it gets separated. Separation can be in same direction or it can be in this direction, but however, you get your P dash is in the negative direction. So P dash value can be more or less. It depends upon whether both of them go in the same direction or they go in opposite direction, separating in opposite direction. But in both the cases, you would see that P dash is relative velocity of separation is negative. That's what you see here. So if you take only one vehicle, that vehicle relative velocity would go like that. There is a point when it is changing from positive to negative, right? So this is the variation. So if you look at in this graph, just let me make this bigger. Look at in this graph. This is V2 and this is V1. So this is greater. That's why it hits it. And in the collision, V1 reduces to V1 dash after separation. So this is that point where the common velocity, you have your maximum dynamic crash, or it is the end of your deformation phase or beginning of your restitution phase, this point. And this point of time is what we were looking at again in the chart, right? Whatever we had earlier. So we are not taking this entire thing. We look at their smaller and what is the velocity with which it hits here, right? And again, you see here, there can be a second case where the velocity of one and the velocity of the other is 0. So this is stationary vehicle. This vehicle goes and hit this, and you would have this scenario. At that time, you see this velocity V2 0, and that changes like that. And this is that event of maximum deformation. And the third case, you can have M1 and M2 head-on collision. So they do have approaching each other. You would see that V1 is positive, V2 is negative because it's in this direction. And then there is a crossover here at common velocity. And this point, you would see changes and you have P dash again, negative direction. So the relationship here is that P dash would be always equal to E into P. And P dash is always negative. P would be positive or can be negative after a point. It depends. It can be negative or it can also be positive. See here in this case, P is positive till this point, till this. After that, it is negative. Right? So in this scale, if you see here, there is a 0 value here. So what is that 0 value? V2 is some velocity in this direction. V1 is in some velocity in this direction. So I have this negative velocity to put here. So there is a velocity 0 here. So this point would be for this V2 is 0 in this case. Whereas in the first diagram, what is the difference? You see, that is also positive, same direction. So you have it here. But it is symmetric curve. That's what you see. This is symmetric from here. It is symmetric curve. And relative velocity, what is that? What is this P? P is nothing but here it is V12. So when I take V12 is what is P? Is V1 minus V2. So that is velocity of this from here, 0 to this V1, 0 to this V2. Absolute velocity is V1 and V2. So V1 minus V2 is what is velocity of 1 with respect to velocity of 2. With respect to that, right? So these are the three cases you can have, and the problem. What I mean by that is, if you have understood Kelvin's theorem, you can find out the energy dissipated for these three cases when you are given from the formula straight away. From the formula straight away means what I say, you know what is effective mass now, ME, M1, M2 by M1 plus M2. And the theorem state delta E dash is delta E into 1 minus E square. Now, delta E is half ME P square. So before collision, if you know velocities, that is the fall that can fall in these three categories. You know what is P. You know what is ME. So you know what is the total crush energy, and you are given that the vehicle coefficient of restitution E value, then you are knowing what is the dissipated energy. So this is how you can find out the dissipated energy. And this expression is derived from the Kelvin's theorem. This is not Kelvin's theorem. This is derived from the Kelvin's expression, where the Kelvin's expression says this delta E dash is simply half IMP into P plus P dash. So this is Kelvin's theorem. And this Kelvin's theorem can be expressed by this from the application of fundamental concepts. And we were able to discuss this. So this completes your central impact. This completes your central impact. So next class, that is after our coming back after your midterm exam, we will see. And that Monday class, I am not taking morning. Maybe I will take in the afternoon because I am not in Vellore. I will be going and coming back. So next class will be Monday afternoon, 2 o'clock, right? Okay, good day to all. If you have any doubts, today's discussion.